I always think about how much to explain when it comes to e to the x, but I think what we'll do today is we'll focus on the calculus version and explain what e is. It's irrational. It's 2.7 something 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 2124 something 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 50 something something 911, my birthday. Any number can be found in an irrational number if you go to enough decimal places. So I'm going to argue to you that you know some of these irrational numbers like pi, whereas no matter how many digits you take, there's more digits to go. That means you can't do like 3 divided by 2 and end up with an answer that's e. E is found everywhere. It's in nature. It's in the algorithm for how trees and leaves build. It's in how water moves. It's in compound interest in banking. You find it everywhere. Rocket science all the way down to snails, okay? But what the heck is it other than the number 2.7 something? It is not just a number. The number represents an idea. And that idea is something like this, where if I have a graph of f of x equals e to the x, you're going to get this. It's an exponential function. In fact, that's what the e is kind of short for other than Euler's number. Exponential function. That means that it climbs faster than x squared, x cubed, x to the fifth, because x keeps increasing. So eventually your exponent's going to be 1,000. It's going to be 1,000,000. It's going to be 1,000,000,000. It grows quickly. And the special property they're telling you here, and this is a part I'm not going to prove for you, but we will look at what this means in a second, is that the derivative of e to the x is e to the x. So that means that if I take a point here and I find the slope at this point, the slope of this line, whatever my x value is equal to 2.7 something to that value. Which means that if I graph the derivative, it's exactly the same as the original. If I graph his derivative, it's the same as the original. If I graph his derivative, it's the same as the original. I can take derivative after derivative after derivative and end up with the same picture. But that's not true anywhere else, right? Because if you think about this for a second, let me remove this out of the way here. If you think about this, we've done some of these problems, right? The graph of x squared is a parabola, but 2x is his derivative, which looks like this. And his derivative is 2, which looks like this, flat line, just 2. So these don't look the same. No other function is going to have a derivative that is itself. That is entirely, I don't want to get rid of that. That is entirely a property of e to the x. And we can prove that. I promise you're going to want me to do it later and not now. That's more advanced. But look at this one for a minute, because this is how they define it in calculus, and this is one that you should understand. The limit as h approaches 0, because doesn't it always, of e to the h minus 1 over h equals 1. So if I give you f of x equals e to the x, and we want to do f prime of x, well, you know how to do that. That's e to the x plus h minus e to the x over h. And if I want to simplify that, remember x squared times x cubed is equal to x to the fifth. If these exponents are in line, they add. Right? It's an exponent to an exponent that multiplies. If I do x squared to the third, you're going to get x to the sixth. That's when they multiply. So as long as they're like this, I can do it backwards, and I can say this, e to the x, e to the h, minus e to the x, all that over h. And then I can take an e to the x out. And that's going to be equal to f prime of x. But guess what? We know what f prime of x is. The derivative, they write it as d dx here, which is important, and we will do that in the future more, is e to the x. So this is all still over h. We have e to the x, e to the h minus 1 like this over h. We can divide this e to the x out. And you're going to find, of course, e to the h minus 1 over h equals 1. That's what this says here. Okay? And because the e to the x has nothing to do with h approaching 0, you can take it out of the limit, and you can put it like this. E to the x limit h approaches 0 like that. See what I mean? So that's just a quick explanation for what E is. But the important thing to remember, and maybe the thing that you're only going to care about going forward, is that the graph looks like this, and his derivative looks exactly the same, and his derivative looks exactly the same. If you can remember this fact, you're going to have a lot of e's, because remember, e to the x is related to the natural log function. We write it as ln because it's log au naturel. It wasn't in English, remember, originally? But these functions are interdependent. So if you remember your logarithms, it's b to the k equals a. And if you want to write that in a different way, it's log base b of a equals k. So for us, no longer is it b, it's e, and no longer is it k, it's x. And that's going to equal a. So here it would be natural log, which is how we write log base e of a equals x. You see how those switch? So instead of writing log base e, because we know it's 2.7 yada 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 irrational number, we write the natural log like that. This is just a very brief way to think about this stuff. You should know natural logs already. You should know that e exists already. But the derivative is itself, and we'll use that in the problem videos going forward.